Okay, fine. So if you recall, is it visible, right? We have seen this particular strip footing, sorry, strap footing, where strap would be there. So now we'll focus on, mat foundation actually. So when we have to go for mat foundation, there are some principles given here. Okay. So here what it says is the overall I will not read out. I will tell you what this paragraph is all about. So generally, raft foundation we will prefer if the soil is soft. Okay, but soft up to what depth? Okay, if it is a very long depth, then we have to go for pile foundation. If the soil is soft for a lesser depth, okay, and in that case, what we'll do is we'll remove full that soil and we'll fill with the mat. So whatever soil we have removed, the weight of the soil or a pressure would be compensated by the raft foundation, the mat what we provide. So increasing the stress, I mean net increase would be zero only, okay, because what we are doing is we are replacing the soil with the mat. So this is the criteria and it is very famous and people are started using because net stress would be zero at the bottom of this raft. And one more criteria is if you provide individual footings, okay, if the area of the individual footing is more than the area of the 50% more than the whole area. Suppose we have some area, whole area, some 100 meters square, something like that. And when you try to provide this footing, if individual footing crosses more than that area, 50 more than 50% of 100 meter square, then in that case, code says it is better to instead of providing these footings at a lesser distance, better to go for a full raft foundations. Okay, so we can bring this that particular footings or columns from the raft and we'll start constructing. And the more advantage of this raft foundation is you can reduce the differential settlement actually because there is no individual footing here. So whatever it settles may not be differential settlement. It may settle whole, the whole raft may settle. And we have seen in the previous chapter that this raft settlement, we are allowing more settlement, right? If you see, look at our the table, the allowable settlement for the raft is more. Why? Because it is all together settling, because uniformly there won't be much damages to the building, no cracks you could see. So these are the advantage actually. That's what it is given in this paragraph. Okay. So what is the raft and other things? Now, and like if you see how to calculate this particular capacity or what I would say bearing capacity of raft and other things, that is already like we have seen previously here also they have given some many people Terjagi, Tenj and many people have given their own formulas. Those formulas are based on the n values. So as I said, this particular n is very famous. Okay, n value, number of blows. Once you get n, so there are so many things you can do it. We can calculate the bearing capacity, you can calculate the settlement, and you can calculate the many things. It depends on the C5 and other things. Okay, when you do MTech in geotechnical engineering, whatever you are seeing, these people they have their own theory from Mehraf and the Tange and other people. They have and Bowles, especially Bowles, also very big scientist. Okay, now what will the principle if the raft on a cohesionless soil, the bearing capacity of a foundation cohesionless soil depends on the uh, width of the foundation. So if you recall our formula, Terzagi's formula, CNC, gamma, DF and other things, for cohesionless soil, this B term would be there. So more is the B, more is the bearing capacity. Understood? That it is just a common sense. That means if the width of the foundation, if you are providing more, you will get more bearing capacity. It will bear more load. This is only for the cohesionless soil, not the cohesive soil. Because in cohesive soil, this is a very important point. Okay, they will ask in the GATE exam also. For a cohesionless soil, the bearing capacity depends on the B value, B, that is the width of the foundation. But in the case of the cohesive soil, we are not depending on this B. That means if you look at the formula, NC, NQ, N gamma becomes 0, NC become 1, sorry, NC will be there, and NC, NQ would be 1, then CNC plus gamma DF only. Here there is no term of B. Recall our Terjaghi's equations. So for a clay soil, B will not affect. That means if you provide whatever size of the foundation, you will not get the bearing capacity. The bearing capacity is not going to increase with the foundation width. This is very important point. Okay. Then what it is given is according the settlement pressure here. The settlement pressure and not the bearing capacity generally governs the design except for a very loose sand. And here if you see, because just I'm showing directly on the book so that you will understand what it is actually. Here if you see, the safe bearing capacity is determined, this Tench fellow, this guy 1962 has given this formula. Here everything is known here. For this W gamma WQ is our water table factor. Already we know that. B we know that. Okay. N we know that. So by using this one, we can find out the net safe bearing capacity, or the safe settlement pressure for a settlement of 25 mm also can be carried out by this formula 17.5 n minus 3 and so on. Okay, again what they have done is, okay, these are the W gamma W, all these things are the water table correction factor. Already we know that. Okay, so here what we are doing, safe bearing capacity we are calculating, and the settlement also we are calculating. Okay, so generally lesser value of this both generally will take, because sometimes if the soil is settling down, so bearing capacity may be high, but settlement may be also high. In that case, what we'll do is the pressure QNS and QNP are in kilonewton per meter square. The smaller of two values is allowable soil pressure. So what we'll do is, the governing criteria for our bearing capacity is, one is settlement, one is the bearing capacity, the shear failure. Okay. So I stated earlier, Ten's equation for the safe settlement is a conservative. So using the Bowell's equation, which is this one, okay. Bowell's equation for settlement of 25, he has given one more equation here. Okay. Bowell has given this here also. What do we have? The only extra term if you see is the RD. He has given this RD value also. How to find out RD also. Likewise, so what we can do is slowly if you reduce this one, this will become like this. And what it says, as the width of the raft is very large, because pressure bulb whatever it forms would be very large. Okay, then what we say that this B plus B dash term can be equal to 1. I mean, because B by B we can cancel it actually. 0.3 plus 0.3 is there still, but what we say that let us make it as a 1. Okay, approximately 1. Then what happens? It reduces to this one. Equation reduces, and for the taking the suppose RD also given the depth factor. Okay, little if you do reduce it to suppose RD if you take 1 and S you take S value if you take it as the 50 mm, then what he says it is reduced to this one. Okay, so equation. So finally what he has done is he reduced the equation to this QNP allowable pressure is 10 N. That means if once you know this value N, okay, we can find out the allowable pressure. That means if you get 10 value and N value is 10 multiplied by 10, the 100 km square. So what do you say? It is a net allowable pressure. That means, so generally what I'll do is sometimes when I go to this is if the water table factor is there, okay, this 10. Otherwise, generally what we'll do is if you take the water table factor 0.5, then this equation become like this, okay. And Peck also given some equations which is equal to 20N and water table factor. Again 0.5, if you take water table factor, it becomes 10. So what I will do is sometimes if I go to consultancy and they will ask us to do some SPT test and all. So when I visit, what I will do is I will just focus on the N values. So N value, suppose it is coming 5, 6, 10 and all, these are loose soil only, okay. If it is getting more than 15, 20 and all, no, so automatically what happens, we can easily guess the bearing capacity. Okay, so though above equations are applicable for N values are between the 5 and the 15. If the values of N after correction is less than 5, the sand is too loose. Okay, for a raft foundation, the sand should be either compacted or a deep foundation such as pile foundation should be provided. For the values of N greater than 50, the above equation gives the unconservative results. So what if you try to understand here, everything we are converting into N values, okay. And here also if you see IS code 6400 for different settlements, here they have again given this values, okay, whole depend on the N values also. So likewise, if you keep on reading, you will get in feel that only N value is sufficient for getting the allowable bearing capacity, okay. So this is all about this, and here one more term is given, okay. So here if you read, as the raft foundation are generally used for the below basement, the foundation are not backfilled, okay, and can be used. So when it is not backfilled, so Q by A, okay, is equal to gamma D of QNA, is it not? So here Q is the superimposed load, A is the area, and the df the depth of the foundation. Now if you see the raft and clay soil, so again this Kempton, this guy has given a formula here. Here Cu term would be there, okay, and the rest of the things are all other notations have been defined above, okay. The safe bearing capacity can be obtained. This is net ultimate he has given. Safe can be get it by dividing the factor of safety, then that we take 3, but here it is given as the IS code says the raft foundation we can be 2.5. Understood? So now that's what it is given. Okay, so look at this one, what it is given. Here the settlement are calculated due to the net increasing pressure. Here this is the net increasing pressure. That means QI by A gamma DF we can deduct it. Okay, gamma DF. Then how to find out the factor of safety? The factor of safety against the failure can be QNS divided by QN. So whatever we have written here, the same thing they have done here, factor of safety. Understand? So that's what it is compensated. So gamma df is equal to the Q by A. That means it is a whatever pressure we are gamma df we are providing, that would be equal to the Q by A. Q is the superimposed load, A is the area of the raft foundation. So the settlement of a mat foundation can be reduced by decreasing the net pressure in the net increase in the pressure. What is the net increase in pressure? 0 only, there is no net increase. For no increasing the net pressure, what is the equation? Gamma df is equal to Q by A, and df is the depth of the foundation we can provide. So very famous foundation. Here there are different types of the raft is given here. So this is the flat roof. It is very important. Just have a look. This is the flat type of the foundation. That means this is normal. This is the flat, and here column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So column like this. So whatever this elevation, and this is the raft foundation. What we are doing? Fully mat we are providing it. From that we are taking these columns, okay, and after the columns what we'll do, we'll have beams. After beams we'll provide a slab which is connected to the beams and columns, okay. Likewise we'll try to construct a framed structure. After that what we'll do, we'll go for a brickwork walls, okay. So wall doesn't carry any load, okay. This is the wall is used just for a partition. Okay, first what we'll do is we'll focus. So this particular raft foundation, if you see all our major cities nowadays, whether it's Chennai or Hyderabad or Bangalore or whatever may be. So whatever high-rise building you could see, this is all rested on a raft foundation because very huge and very the height of the buildings are, I mean, 100, 200, 300 meters. Okay, so in that case, to avoid differential settlement, we are going for a raft foundations. Okay, if you go and observe it, okay, so many shopping malls also, if you see in Hyderabad and many places, are rested on this raft foundation. And our world tallest building, Burj Khalifa, also on the raft foundation, pile raft, that was on the pile raft. Okay, below that, that also is there. Here I will show a picture. And second one is the flat plate thickened under. That means here what we'll do is when this column load carries more load, so this raft would be thickened here. This is around the column. Okay, these are the columns. Okay, around the column it will be thickened. So when the column loads are heavy, this type is more suitable than the flat type. A portion of the slab under the column is thickened due and to provide the enough thickness for negative bending moment and a diagonal shear. Sometimes instead of thickening the slab, a pedestal is provided under each column above the slab to increase the thickness. This is what their meaning is all about. Okay, so pedestal can also be provided. Now what, sorry, this one only. Now beam and the slab construction. Now what we'll do is, in this type of the construction, the beam run in two perpendicular direction and a slab is provided between the beam. The columns are located at the intersection of the beams. This type of foundation is suitable when the bearing stresses are very high because of the large column spacing and the unequal load. Again, it is strip kind of footing. Okay, at the bottom anyway we have this slab, what do you say, raft, but if the columns are very far, then again what we'll do is it will be connected with the beam, so that beam will reduce the bending. Okay, if all the beams are connected properly, then what happens, this column is not going to settle single. That means everything is connected. Okay, so everything is connected, so everything will try to sync together or settle together. Other nobody will try to settle. Okay, so there is no. It is a group. It is a group. Okay, so there is no possibility of only single column going to settle down and have will causes the cracks in the building. If they settle, they will settle all together. If they don't settle, they won't settle. Okay, so it's everything would be connected here. So it is a group columns. Okay, connected with the beams and up. That's the meaning of that. And if you see this one, sometimes below this raft, we will provide these boxes. Okay, so we have a lot of research is going on in this area also, how what generally these boxes are for and so on. So it is found that for earthquake loading and a dynamic loading, these box kind of footings are very below the this one are very helpful because it won't what do you say, passes the waves, no, with this gap. So waves, dynamic waves, cyclic waves, load can be reduced. So this kind of raft with the box are very important, and this box of structure is provided in the basement which acts as a stiffen for the mat. Boxes can be made cellular construction or rigid frame consisting of the slab. Okay, and this type of mat foundation can resist very high bending stresses also. So there will not be much bending stresses with that. And this whatever I was talking is there Burj Khalifa, the building, they have provided this raft with the piles. Pile foundation, we know that, right? So whatever we are talking about that one, without pile only, all these whatever see is the shallow foundation with the raft, shallow foundation with the raft here. But if you don't find any hard strata, like in Middle East, where the soil is very sandy and the loose soil, okay, Burj Khalifa, Dubai, or whatever Middle East, whatever country, if you take it, Middle East, okay, Egypt or whatever maybe. Here, if the soil is a sandy soil, loose sand, because it's a full of desert, okay. So in that case, they are in a search of finding the hard strata, but hard strata may be very, very deep. So in that case, they may go for a friction piles, and they have so many other techniques to improve the soil. In that case, what we'll do is we go for this particular foundation. That is the pile, okay, pile plus mat, the raft, okay, below the raft we will go for a pile foundation also, very deep. Okay, if you see the Burj Khalifa's uh, foundation, it is very, very deep. Okay, I don't remember how much deep it is, but once I was seeing some video clips, so they have provided how this construction has happened, and it is really difficult actually. So they takes the challenges because it is a very rich country now. They have a lot of money, so that they can no, they can take a risk, and they want to build and show to the world that they can build uh, this one highest building. So that's how they take challenges. And who are working there in the Middle East? Our Indians only. Most of the people, like Indians or Europeans or some of people only, because these people, they may not have that much knowledge about all these things. So they hire, they pay more for us, and we'll go there and work. Okay. So likewise, architecture, whatever you take, the soil, pile, foundation, and the people, these are known people only. I mean, from Indians. So likewise, that's how we are constructing the uh, pile foundation. So there are methods actually how to design it also, general design. So one is rigid beam method, simplified elastic method, and the non-linear elastic method. So this method you will study when you do for MTech, okay, in soil mechanics. So rigid beam method, which is simple, okay, that's what it is given in your book. This method in the of a design, the slab is considered as infinitely rigid compared with the soil. Okay, so flexural deflection of the mat in this case do not influence the contact pressure. Here, one more method is the simplified elastic method. In the elastic method, what generally happens is uh, you read it. Okay, just I'm telling you because when I have done MTech and in this geotech. So what we'll do is we'll consider the soil as a spring, bottom as a soil as a spring. And what we'll do is we calibrate the stiffness of the string and so on, and we'll just uh, use this Winkler's model. So Winkler's model is very famous. What he says is the soil will act as a spring, and he will convert that particular mechanics in the mathematical form, and he will try to solve those equations, and he will give the design. So likewise, there are so many methods. And finite element method, we can use the software like Plaxis 2D, 3D, and many software, Flat 3D. Many software we have, soil mechanics software we have. We can use those softwares, and we can design it actually. That is the non-linear elastic method. Elastic method, you know that, okay? In this method of design, soil is considered as elastic, linearly elastic of space, okay? The method uses the solution provided by theory of elasticity. The actual soil do not behave like elastic because we assume such certain things, that the soil is elastic. Elastic in the sense, when you remove the force from the soil, it will come to original position. Will it come to original position? It won't come, because soil is not elastic, it is a plastic. Okay, So we assume that in that particular method and we'll design a raft foundation. And non-linear method means we assume that soil is not linear, that means not elastic. In this case, what we'll do is we have so many methods like finite element, numerical. Here, whatever you see, no, this method represents the behavior of a soil. Here, the numerical techniques such as finite element method, like that FEM. Well, are you studying FEM?
No, sir.
Do you have FEM in your final year? Elective or something? You may be having finite element method. Okay, it's very interesting. You can read that particular uh, subject. So we use this FEM analysis nowadays. No, uh, we can use. Have you learned the plastic software?
No, sir.
No. So anyway, so some softwares are available in our NIT and in our MTech student scholars are using it. So what you do is we can exactly model in the software. Okay, we can use software and we'll try to apply load and we'll try to find out the stresses in this raft and the beams, column, stat pro are there. So nowadays we are not doing anything conventional or manually. Everything is done by the computer. So we have so many softwares like StatPro, and we are drawing like CAD and other people Revits and other things for the drawing, and for calculating the pressure, pile foundation, other things. We use the Plaxis software. So I have used this particular Plaxis software for my PhD work. So I have worked on the pile foundation only. Okay, my topic was. So what we'll do is directly it will give when you try to apply a load, it will give the bending, shear, and deflection and other things. Whatever you see, read in your uh, mechanics of solid or structural engineering, right? WL by 3I or 8I, something whatever you have bending moment shear, when the beams are fixed, when the beams are hinged, when the beams are propped and so on. So everything you will get it by software nowadays. So this for our conventional things, just I'm explaining, but if you use a software within a no time, you can design it, you will get the stresses and where the beam is more stressed. Okay, it will show with the colorful pictures. Okay, so here conventional design is given here for a raft foundation. Okay, so according to American Concrete Institute, the design of a mat foundation should be done using the conventional method. So in this book, they have not given this one. Only one is given. And for undergraduate level, this is more than enough actually to understand this raft and all. So here, if you see, the design of mat foundation should be done using the conventional method if the spacing of the column is a strip as raft is less than the 1.75 by lambda. Okay, meter using the simplified elastic method when it is greater than that one 1.75 where gamma is also is given. Okay, so here conventional methods are given. We use if it is more than that this values 1.75 we use the simplified elastic method. So this lambda is given, what is lambda, what is b1, k, all these things also given here. Okay, q by z and so on. If you see design procedure here, okay, let me check it. This is just to classify one. So what is the design procedure actually we follow it? If you see that these are the Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, Q9. These are the suppose columns 1, 2, 3, 4, 5, 6 columns. And if you see here, uh, anyway, for our engineering mechanics is very important here. Whatever load you are getting, it should passes through the center of gravity of this raft. That means we have 1, 2, 3, 4, 9 columns we have it. So whatever load is acting up this 9 column, when you try to calculate taking the bending moment or like what we do in engineering mechanics to calculate the uh, center of gravity, if it is not passes through the center of gravity of this raft whole building, then what you see, you will see eccentricity. So that's what we have taken this case. This the CG is here Q. Okay, and EXCY is the from here at what distance it is acting. So CG is not going through this one Q5 here now. Understand? So Q is the center of gravity. In that case, what generally we do, there are procedure given. First procedure is just we quickly will follow one by one, 1, 2, 3, 4, 5, 6, 7. Okay. Now, once we'll see the numerical, you will understand actually. It may be a little confusing and may not giving hope you that how to design a foundation. But in next class, what we'll do is there are some problems are given in the book, a solved problem. When you look at those solved problems, we will understand actually what generally, how generally we will design a foundation. But the only thing is you should be thorough. Sorry. Excuse me, yeah. Please mute your this one. So only thing is you should be thorough with your RCC actually. Because here we are not discussing anything reinforcement, how to provide, how much and all. So what we'll do is we'll give a length and depth and all, and we'll ask to find out the shear bending and find out the reinforcement by using our RCC. So that's what it is given, because this book has been limited. Otherwise, it would become a RCC book. Okay. So we'll just focus on the bearing capacity only here. So now, if you see here, first determine the line of action of the load acting on the raft. The self weight of the raft is not considered, okay, and it is taken directly by the soil. So first what you do, determine the line of action. So determine the contact distribution as under, okay. So contact pressure, what we have to do, you have to determine. How to determine? If the resultant passes through the center of the raft, the contact pressure is equal to Q by L. This is load divided by area of the raft. Suppose if it is not passes through, then we have to take the help of this EX and EY. If the resultant has a eccentricity here like that, so in that case here, this moment, whatever QA X by IY. So if you look at our formula M by I, okay. So those formula we have to use it here. M we have to use it plus or minus, and we can find out the contact pressure. Okay, once you find out the contact pressure, what we'll do is the maximum contact pressure should be less than the allowable soil pressure. So whatever contact pressure you will get, it should be less than, right, to the allowable soil pressure. So divide this slab into strips. Here, very interesting thing. Okay, if you see here, this is the full raft and it is divided into strips. What are those strips? B1, B2, B3. Some strips have been divided here by taking this one. So what we are doing, we are simplifying it. So we are not taking a whole raft. What we are doing is we are just simplifying it. So divide the slab into strips, bands in X and Y direction. Each strip is assumed to act as a independent beam subject to the contact pressure and the column load. So what we've done is we have again brought it to beam here. Again beam design. We are dividing into strips. Okay, then these strips are, if you see, look at the second picture. So these are the column loads. Okay, suppose these are the column load. This is the contact pressure on a beam. So this is very easy to design and very easy to find out the shear force, bending moment, and other things we can do it. Okay, same thing you can do it, and we can design a full raft foundation. Okay, so draw the shear force and bending moment diagram. Then determine the modified column. That means actual. Okay, modified column as explained below. So here it is explained the average, how we have to find out. Here generally let us consider strips of Q1, Q2, Q3, and B1 is the width of this strip. And let us find out the average contact pressure. That means downward is equal to upward and all. It has been found. Okay, so likewise what we'll do is we can design this whole strip raft foundation by making a small strip with acting of a load. Once you know that one, this is the soil pressure, we'll take it as a UDL load. Okay, you can reverse it also. What will happen if the reverse it? 1 2 3, this particular beam is resting on a 3 columns or a point loads. Okay, and passing through the UDL. UDL, we know that how to draw shear force and bending moment diagram. That once you draw the bending moment diagram, we'll get an idea that maximum from the maximum bending moment diagram how to provide a reinforcement, how much reinforcement we have to provide, and where to provide to resist. So this is all whatever you see here. Finally, we are trying to make it as a beams. Okay, RF. This anyway we have seen the footing and we are converting it to in a beams only. Then we can design this all this foundation. So once you see this particular what do you say problem, then you will understand. So that's the reason. So once you see a solved problem, you will get a confidence that yes, we can design a footing easily. So now what you do is you read it once. It's not very difficult. Okay, try to understand it. One reading is more than enough because some people are given direct formulas like Tenge or a Skempton or a Mehrab or a Bowles. They give direct formulas because they are so confident on the n values that once you, because everything is related to n values only. Once you have n values, so that's what we do in the uh, consultancy work. If they ask to come and investigate, no, recently we have done for our Trichy airport. Okay, so there is an extension is happening to Trichy airport. Okay, they have called for the soil testing. So what we have done is, first soil testing means SPT value. SPT will find out the SPT. Once you know SPT and we'll bring the soil sample from the field, we can classify those soils and we classify that in which zone it is falling the soil. And based on that, if the gravelly sandy soil, definitely you will get the very good n value. From that we can use some equation. IS code has given equation and Boyles has given it. We can find out the bearing capacity. Once you know bearing capacity, so it will give that and what kind of foundation we have to go. If it is very soft, we will suggest them raft foundation. Okay, if it is loose soil, or sometimes we will suggest for the pile foundation if we get the hard strata or the n value rebounds. That means if it is going more than 50 60 and all, 50 is enough. Okay, more than enough. 50 and value is more than enough. So then what we'll do is we'll design a foundation. We'll say that please go with the a foundation, a pile foundation. You will be safe. There won't be any problem. If it is a loose soil and if you find that soil is wearing, then what we'll do is we'll ask them to remove whole soil and go for a raft foundation. So as a geotechnical engineer, what we have to do is we have to visit a site and we try to understand if some construction or temples or guest house, many things are housing board, the CPW, PWD, this department. So continuously they are constructing some buildings. Okay, and they will approach to NIT and we sometimes we will go there and we'll investigate the soil and we'll suggest some foundation. Okay, which is suitable for that. So this is how generally it will work. Okay, so I would have shown some SPT test also. Okay, because sometimes we go out, but you guys are not in NIT Trichy now. Okay, so it's very simple. You can check in the YouTube generally how generally find out the bearing capacity, how generally foundation can be designed. Okay, so many videos are available nowadays. Okay, you just learn it if you are interested. And with that, I'll stop today and keep reading it. We have one more class on this particular chapter. After that, we can have an exam. You guys can decide when we can have exam. Maybe next week or next week. Some date you please give me. Okay. And as like first city, everyone should be present. Okay. It is again a multiple choice questions. Both of this chapter, bearing capacity and design of this foundation, are included. I'll give you enough time. You take 1 week. If you want 10 days, also take it. Read it and learn it, and we have one simple exam. Okay. So with that, I'll stop today. So let us hope you will understand this particular chapter, because some of the things no they have given directly without any no derivation and all. So sometimes we have to accept it because based on the research and the this one in the book these formulas are given. Okay, so if you refer the journal papers, no, so they will give you a clear cut how you will got all these things. So that much research is not required for you undergraduate level. Okay, some of the formulas which are important to you and for your competitive exam, those formulas only you just remember it and try to understand the concept actually. That's more important. So with that, I'll stop today. We'll meet in the next class. So shall I close the meeting?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you.
Thank you, sir.
Please read. There is no shortcut. Okay, please read. One reading is enough. Okay, I know you may not be following the class because I know that you don't read every day. That also I'm aware, but try to read at least for before exam. Try to read it. I try to make a simple question paper only. Let us see. Okay, I'm closing the meeting.